space with two balls, just like part A, except this time when the astronaut shoots the clay ball, he hits one of the sides of the rod instead of the center of the rod. So part 1 is to find the center of mass after the clay ball connects with the rod. So the center of mass is just the sum of all of the mass times radii over the total mass. The first mass is just this ball times the length. Since we're finding it from the left, the length is 0. The second mass radii is after the clay ball connects with the right side. It will have a mass of 2m because it's m plus m, and it'll have a length from the left side of L, which is the length of the rod. The total mass is 3m because every piece of the system has m and the rod has a negligible mass. You just add that all up, you get 2 over 3L. So the center of mass is about here, right, 2/3 from the left side. Part 2 is to indicate the direction of the center of mass for this system. So it's just up because the center of mass moves in a straight line. Well, not necessarily a straight line, but it moves along a path. It doesn't rotate like the sides do. And the ball is going in this direction, so it's going to impart a velocity in this direction. Part 3 is to find the speed of the center of mass. To do this, we use conservation of linear momentum. On the AP test, you get a point for this, so make sure to write this, pi equals pf. The initial momentum is the mass of the clay ball times the velocity of the clay ball, which is v sub o. The final momentum is the mass of the system, which is 3m, as stated before, times the final velocity. Just solve for the final velocity. You get v sub o over 3. So the final velocity is 1/3 that of the initial velocity. Part 4 is to find the angular speed of the system. To do this, we use conservation of angular momentum. Li equals Lf. Make sure to write this on the AP test because you get a point for it. Well, angular momentum is I omega. So I omega initial equals I omega final. I omega initial is m times the r, length from the side, which is L over 3 squared, times the initial velocity, v sub o, over r, L over 3. The r cancels out the squared, so the initial momentum is ml v sub o over 3. The final, you have to find I, because there are 2 different parts to this. You have to just find the sum of the i's, which is mass times 2/3 the length, because this mass is 2/3 the length away from the center of mass, times length squared. This one is 1/3 away from the center of mass, so it's 2m times 1/3 L squared. You just add that up, you get 2 over 3 ml squared times omega final. Solve for omega final, you get v sub o over 2L. Part 5, the final part of this long problem, is to find the change in kinetic energy. To do this, we take the final kinetic energy and subtract from it the initial kinetic energy. Kinetic energy, because there is both linear and angular movement, you have to do the linear kinetic energy plus the angular kinetic energy. So this is the initial, this is the final, this is the final, this is the initial. Although initially there is no angular movement, so the initial angular kinetic energy is 0. So kinetic energy final, 1/2 mv squared for linear is linear kinetic energy. It's 3m because at the end the mass of the system is 3m. V final squared plus 1/2 I omega final squared minus 1/2 m v sub o squared, since omega initial squared is 0, since omega initial is 0. So we get 3 over 2 mv final squared plus 1 over 2. You take the I from this part, as we found before from this, times omega final squared minus 1/2 mv sub O squared. This is still final kinetic energy, initial kinetic energy. You just use addition and subtraction, find the common denominator, which is 12, and then simplify your final answer, and you get negative mv sub O squared over 4 for the change in kinetic energy.